Okay, in this very last podcast that I am making, we're going to go over oxidation reactions. So we've looked at a precipitate reaction, and that's one that forms a solid in the product, acid-base reaction, which forms water in the product, and oxidation is unique because basically we're going to oxidize and reduce something. So what does that mean? Basically means we're going to exchange electrons, okay? So some, let's say, compounds or elements are going to increase their number of electrons, and some will reduce their number of electrons. Okay? There are certain oxidation rules, okay, to get an oxidation state. So oxidation is really based on this concept called electronegativity. Let me pull up, a periodic table here. Right here. Electronegativity, and we'll go over this later, but it basically means you love electrons. So you're going to want to steal them away. And the trend of it goes, basically fluorine is the most electronegative atom. So whatever atoms are closest to fluorine, those are going to be more electronegative. So like oxygen, chlorine, those are very close to fluorine, so they're going to be very electronegative. So they love electrons, so they want to steal them away. You see over here, like sodium, magnesium, all of these over here, these are very far from fluorine, okay? So they don't want to steal electrons. They want to give up electrons if you want, okay? So oxidation state is this sort of hypothetical state that you get whenever, two things bond together. So what in the world am I talking about? Let's look at water, for example. Okay, water. Water looks like this. Lone pair. Okay. Water looks something like this whenever you draw it out. Now, these are covalent bonds, so all the electrons are shared. But hypothetically, if we pretend it is a ionic bond, what would be the oxidation state? So what would be these hypothetical charges? Okay. Now, again, let me reiterate that this does not happen, but in a hypothetical state, what if it did? Okay. Now, what you do is basically there's no sharing of electrons, okay, in the oxidation states. We pretend everything is ionic. So we look up on the periodic table, what is more electronegative? And look at this bond first, hydrogen or oxygen? Okay, so let's look at the periodic table. Here's oxygen, here's hydrogen. What's closest to fluorine? Okay, that's oxygen. Okay, so oxygen will steal all those electrons away, okay, because it is electronegative, meaning it likes to steal electrons. So remember, okay, so these are electrons, so it's going to steal these electrons away. In a bond here, that's 2 electrons. Now same for over here, it's going to steal these electrons away. Okay? Now let's look how many electrons are around it. 1, 2, 3, 4, 5, 6, 7, 8. So on the periodic table, oxygen should have 6 electrons, but now it has 8. So how many did it gain? 2. So basically it stole the electron from this hydrogen and stole the electron from that hydrogen. So it gained 2 extra electrons. So instead of 6, it gained 2 extra electrons if we want. Okay, so now it has 8 electrons. Okay, so we have, this is a -2 charge. Okay, but these lost an electron. Okay, what charges are electrons? They're negative charge. The electrons, are a negative charge here. So if it lost a negative charge, it became a +1 or a +1. So those are the oxidation states. So if this was, hypothetically, an ionic compound, oxygen would have a -2 charge, and hydrogen would have a +1 charge. Okay? And that's how they come up with the rules, okay, based on electronegativity. But let me give you the basics here. What oxidation states things typically have, okay? Because you're not necessarily familiar with how to write this out and count electrons and all of that. You don't know how to do that yet. You won't know how to do it until near the end of general chemistry. So how do you do this without drawing it out? Well, there's common oxidation states, okay? Elements in their natural states have an oxidation state of 0, okay? So if it's just aluminum solid by itself, it's not bonded to anything, okay? It's 0. All right? Oxidation states of ions are the charge of its ions. So if I say that you have sodium plus 1 charge, that means the oxidation state is plus 1. Group 1 metals have an oxidation state of plus 1. And that's basically its charge, if you would have given it a charge. Group 2 metals have a plus 2 charge. Group 3 metals tend to have a plus 3. Hydrogen, hydrogen tends to have a plus 1, but it can have a negative 1, so, but it's typically plus 1. Fluorine is typically negative 1, and oxygen is typically negative 2. So let's look at this. Okay, so all of these in group 1 tend to have a plus 1 charge. And that's the oxidation state too. Group 2 tends to have a plus 2 oxidation state. Group 3 tends to have a plus 3. Fluorine tends to have a negative 1. And oxygen tends to have a negative 2. Now everything else you can figure out. So let's do this example here. HClO4. And we want to know the oxidation state for every element in that compound. Okay? So we have HClO4. And I say, what is the oxidation state for every element? Okay? Well, according to our rules, hydrogen equals to plus 1. Okay? Oxygen is typically a minus 2. Okay, and that's just from the chart. And we need to figure out chlorine. I did not give you a rule for chlorine. You're probably tempted to say negative 1 because it's in group 1. But if I look back at the rules, I did not say that. I said fluorine is negative 1. Okay, not everything, not all halogens are negative 1. So let's figure out what chlorine is. Okay? So we just figure this out. So I know hydrogen is a plus 1. So I have a plus 1 for hydrogen. We don't know, plus 1. We don't know what chlorine is, so I'm going to put plus chlorine. We don't know what that is yet. Plus, we have 4 oxygens, right? That's what it says, 4. And we know all those oxygens have a negative 2 charge, or oxidation state. And overall, what is the charge of this compound? 0. If there was a charge, it would be written up here, okay? But there's not one, so we say this, when we add all these together, they need to be 0. Okay, so let's see what we have. We have a plus 1, and 4 times 2 is negative 8. So we have plus 1 plus chlorine, we don't know what this is, plus a minus 8 equals to 0. Okay, so let's add these together. Plus 1 and a minus 8, that's going to be a minus 7, plus chlorine equals to 0. We're trying to solve for chlorine. So chlorine, we bring the minus 7 over, it's become a positive, equals to plus 7. So the oxidation state of chlorine is plus 7. So that's the hardest one. We know what hydrogen is, we know what oxygen is from our chart, but then what's chlorine? We have to solve for it. So that's how you figure out oxidation states. So this is, okay, basically, if we pretend that every single compound is a, sorry, every compound is ionic, what sort of quote-unquote charge would it have, okay? And again, we go back to this sort of rule thing here. This is what they almost always have. So, 95% of the time, group metals will have a plus 1. Group 2 metals will have a plus 2. Group 3 will have a plus 3. Hydrogen will have a plus 1, sometimes a negative 1. Fluorine will have a minus 1, and oxygen will have a minus 2. So based on that, we can solve for everything else, like we did with chlorine. Okay, so the next one will be from Khan Academy, and he's going to go over more examples of these. Okay, well, let's actually do these. Cl2, you see chlorine's not bonded to anything else, it's just bonded to itself, so the oxidation state is 0. So if we come back here, you see, if you have a compound that's only bonded to itself, then it's 0. Sodium plus, okay? Sodium is a plus, it says it's a plus charge, so the oxidation state is +1. It's whatever it says it is, okay? Kf. Well, K is in group 1, so we know it's going to be a +1. Fluorine is, I said on here, fluorine is -1, so it's -1 oxidation state. So potassium is +1, fluorine is -1. Let's look up CO2. Now this one's a little bit harder. CO2. So we're trying to figure out the oxidation state for every single atom on here. So we have CO2. We know oxygen equals to -2 from my chart I gave you. Okay, that's one we do know. But I didn't give you anything for carbon, so we need to figure out carbon. Do you see that overall it's neutral because there's no charge there? Okay, so we have carbon, we don't know what that is. We have 2 oxygens, and all of those oxygens have a -2 oxidation state. And overall this is 0. So let's figure this out. Carbon, we don't know. 2 times 2 is a -4, because we have a negative there, equals to 0. We bring the 4 over, so carbon is 4. So the oxidation state of carbon is 4. Let's do another one. I don't know why. Awesome. Now everything is stopped. Escape. Okay, so let's do SO4 2 minus. Okay, so we have on here SO4 2 minus. Okay, again we know oxygen equals to -2. Now overall, you see I have a charge now, overall it's going to equal to -2. So I have sulfur plus 4 oxygens, because that's what it says right here, multiplied by a -2 equals to -2, because that's the overall charge. Okay, so now I have sulfur plus a -8 equals to -2. Bring the 8 over, so sulfur equals to a +6. Okay, so that's how you do oxidation states. The next one will have more examples, and then after that we're going to apply them to actual reactions. Okay, so how do I know? I can do individual molecules, okay, but how do I apply that to a reaction? How do I know if something's a redox reaction? Okay, so and basically what we'll do is, now that we know how to solve and figure out the oxidation state of everything, now we're going to look, does that oxidation state change? Okay, so if I go from a carbon on one side of the equation is a +4, but on the other side of the equation it has an oxidation state of -2, do you see that then it reduced? So that we say carbon was reduced. And so it'll go over that and apply this to an actual equation.